Okay, good morning, guys. As you know, we were discussing data structures, and today actually I want to cover the whole chapter since this is the fourth week and we should have actually started another chapter on a different topic, trees and analysis of algorithms, but unfortunately we couldn't finish this previous chapter. So in this 2 hours, I plan to cover the data structures completely. Okay, these were things we discussed. If you have questions from the previous topics, please stop me. We discussed these stacks, text operations. We discussed some examples and then switch to infix, prefix, and postfix expressions. We discussed how to convert a given expression, infix expression, to a prefix and then postfix expression. And then discuss an algorithm which is converting the infix expression to a postfix one using stacks. And we also worked on an evaluation algorithm of postfix expressions. This was an example. And I think we were left right at this point. This is the second type of linear data structures actually we are going to cover in this chapter is queues. And again, it's a linear, and this time we are not actually just working on the top. We can also add some items from the from, but the removed items will be the ones actually which are at the back side or which were put first into the queue. So we can say that this is a first in, first out type of data structure. And there are many examples in our real life. The lines we have for a movie or checkout lines at groceries or your music playlist. The one actually you put first will be played out first. Or any case you have in your printer tasks, you may send many papers, many PDF files, let's say, into your printer, and then it will start printing the first one it gets. So we can say that it's an first in, first out type of implementation. And what are the operations we need to have with this data structure? First of all, we need to create this data structure. This is for initialization. And then we have an enqueue type of operation. With this one, you add items into your queue. And with the queue, you simply remove the item which was actually the oldest item in your queue data structure. And then we have simple ones, checking whether the data structure is empty or not. And the last one is checking the size of the data structure. So here you see an example. We have similar items as it is in the stacks data structure. So we start with an empty one. We create an queue data structure by using this queue operation. And after that, the first operation is about the emptiness. We are checking whether this one is empty. Yes, it is empty. It's a true. It returns a true value. And once you start entering some inputs to this queue, as you see, the first one is 4, the second one is a string dog. So we will have the oldest item 4, and then we have a newest item dog. And then we continue adding one more, a true value. This is now the newest one. Right? Once you check the size, obviously it will return a value of 3. And now it's not empty, obviously. If you check it, you will see that your implementation will return you a false value. And then you continue adding an extra item, 8.4. Now, this time is the first time we are using the queue operation. As you see, if you remove an item, it will be the oldest item in our queue data structure. So if it was a stack data structure, once you do the pop operation, it will pop 8.4. But right now, since it's a queue data structure, it will pop over the queue the value 4. And once you do it once more, we will have the doc actually popped. And after these the queue operations, we can check the size and see that obviously it has just 2 values. This is a simple implementation in Python. And again, since we are using Python, we need to use the list data structure, the original data structure of Python, to create a queue data structure. So the first operation is the initialization. So we create an empty list, and this is for the empty operation. We check whether the list is actually equal to an empty list. If this is true, then it will simply return a true value, and we will understand that the queue we are actually playing with is an empty one. And then this one is a bit different. Here you see we start adding items with this enqueue operation. It's a bit different than the stack data structure. If you remember, once you add items and a stack data structure, we were simply using an append operation of the list data structure, but that right now we cannot use that. Since once you append an item, it will be at the top of the, let's say, list, and once you do the queue operation, it will be quite difficult. So that's why once you add an item, we try to put it at the, let's say, base of our list, so that once we do the pop operation, it will be highly easier for us, and we will just simply remove the topmost item, and this will be the oldest item in our queue data structure. And the newest ones are always insert at the 0 position, 0, let's say, index of our list. And lastly, this is very similar to stack data structure. The size is the same as the length operation of original list data structure. Any questions, guys, about the implementation? No questions? Okay, so then tell me the answer to this question. What items are left in this queue? We have a queue data structure. We are adding 3 of them, and then we have an extra operation, a very simple one. So let me show you. So once you do the first enqueue, we will have an hello here. And then once you do the enqueue, doc will be actually inserted into the 0th, let's say, position 0 index in the data structure. So doc will be here. If this is the data structure, the list in our Python implementation. And once you do another enqueue operation, this value will be inserted into the 0 index, and 3 will be here. So hello is the newest, the oldest item, and 3 is the newest item. So once you do the queue operation, obviously this string will be popped and it will return. So we can say that this is equal to a string of hello. Okay, this is a very simple question. Now we will see some more complicated examples where we can use a queue data structure. And we prefer to use actually these data structures usually mostly in simulation type of tasks. And here's an example. We have a game called Hot Potato. So what is that? We have a kind of a circle, as you see. There are people, there are some children playing this game, Hot Potato. And then we continue, let's say, we have a hot potato in one's hands actually, and then once the turn is actually over, then it will pass this hot potato to the next child. right now this is Bill, and after you play it one more, Bill will pass it to David, and then this will go on, and at some point you will stop. For instance, you will say that we have 14, let's say, passes, and then once you do that, it will be stopped, and the child actually which is holding the item, for instance, let's say that when we stop this process, Susan is holding the hot potato. Then we will be removing Susan from the game, and we will continue with the remaining children. So this is the fundamentals of hot potato game. And for the simulation, as I mentioned, we will be using a queue data structure. And obviously, we will be actually the names of the children will be in the queue, and the child holding the potato will always be at the front of the queue. Since why is that? Since when we stop, we will be removing the child having the hot potato. So if you use a queue data structure, that will be the topmost item, and we will simply pop it, and then that child will be actually removed from our game. This is another illustration. So you can have a kind of a linear representation instead of a circular one. So Bill is at the front right now. Obviously, we will remove it and then put it at the back. So this is how we do the simulation. We need to have a queue class for the data structure we are going to use. And this is definition hot potato we plan to use in our simulation. So what are the inputs? We have the list of names, as many as you like, and then we have the number, and this number is representing the number of simulations. So for how many times we are gonna do the simulation. So what we do first in this definition or in this operation, we simply create a data structure, a queue data structure, and this is named as SimQ, simulation queue. And then we simply put all these names, put all the names in the name list into the queue data structure, and we do it with the help of enqueue operation. So it's not a complicated task. You can assume that these part as an initialization part. And then here comes the main simulation part. Here we are using a while loop, and it starts with checking the size of the simulation queue. If the size of the queue is higher than 1, larger than 1, that means we have more than 1 children in the queue. If that's the case, then we can play the game here. So what we do, for the given number of, let's say, operations, we do some removing and adding operations. So as you see, we have 2 operations inside each other. We first docu the name in our actually data structure, which is the oldest item in our queue data structure, and then add it into the data structure once again. So we are removing and then adding this name to the end of our, let's say, linear representation here. Bill is removed and he is added to the rear side of our data structure. So after we run this simulation or play this game for the given number, and then what we do, we simply remove the guy actually who is holding the hot potato. So this is done with the help of the queue operation. Then what we do, now we have 1 less actually children remaining in our queue data structure. Initially, assume that there were 6 children, but once you are done with the first loop operation, first for loop is completed, you will remove the guy holding the hot potato, and you will right now have just 5 of these children. And since 5 is larger than 1, we will run it once again for the given number, and remove one child again and continue this game until we have just one child left in our Q data structure. And finally, if the number of children left in this data structure is 1, we stop this while loop and return this child who is left in the Q data structure. Any questions, guys? So I may share you the Python now here and do some simulations. So right now, as you see, we have again 6 children here. I'm running this for in a single, let's say, run of the game. We'll be removing and adding these names into our data structure for 7 to 8 times, but I may decrease it to, let's say, 5 and then run it once again. This time, Jane is removed. And if you make it, let's say, 12, this time Susan is actually removed. Okay, any questions, guys? So there's a question about which loop, Ahmed? We have many loops here. One loop here, another one here. Okay, you mentioned about this one. So here actually we are simply assume that this is our linear. I think I better use a white one. Yes, this is our linear data structure. What we do here is simply remove the child actually at the front of the queue and put this guy to the end of the queue. Remove it, put it at the end. Remove, put it at the end. And we do it for the number of times given here. Even though we may have, let's say, 6 children here, this number might be 4. So which means that we will be doing this operation for 4 times. And after that, the one actually at the front will be holding the hot potato. So at this point, at this statement here, we will remove it and he or she will not be anymore in the game. That's why it's called as hot potato. After this number of returning or operations, we remove the guy holding the hot potato. And then we will have just 5 children, and you still have the number equal to 4 here. So again, we need to run it for 4 times. And with this expression, we'll be removing again the guy holding the hot potato, and he or she should be at the front of the queue. Any questions, guys? So we have 2 parameters actually here in the simulation, the number of children in the game and the number of actually simulations we should perform for before removing a child from the game. Is it clear, Ahmed, right now? Okay. We have another implementation, another example where we use a Q data structure. This is a bit complicated than the previous one. This is about printing some documents. And assume that we have about 10 students and they're in the same lab in the same hour, and they actually do twice printing operation in this time, and the length of their documents, the size of the number of pages of their documents are in between 1 to 20. So we have 10 students, they are printing twice in an hour, and the length of their files are in between 1 to 20. And the thing is that we are actually trying to find the best printer in terms of the speed. And right now, we may assume that the printer is processing actually 10 pages per minute in a draft quality, not in excellent quality, but in draft quality. The printer right now available in the lab is capable of printing 10 pages in a minute. And once you actually implement this simulation problem, then you can try to find the best printer so that no one will wait actually for their documents. If you, for instance, increase the speed of your printer, let's say to 100 pages per minute, then that means probably no one will be waiting for their documents to be printed. But if it's a very slow printer, let's say 2 pages per minute, then probably students will be waiting for their documents to be printed. Since we have many students in the lab and they are printing twice in this hour, and the length of their documents are quite high. So our question is, what is the optimum page per minute for the printer? And the thing is that we are trying to find the optimum one, since you may directly get a printer having a page per minute property of 200, and then the printer obviously will be too costly. So we try to find the optimum one so that its cost will not be that much. So this is a graphical illustration of the problem. We have some number of students using their computers or computers of the lab, and then they submit some tasks, submit some documents to the printer. And the printer actually must use a queue data structure, since it needs to print the oldest item in the queue, and the newest one will actually have to wait for the earlier tasks to be printed. So for the nature of this problem, a queue data structure should be utilized. So how we are going to determine the average amount of time the students are waiting? So we can have such a multiplication and determine the waiting time for a task. So you may say that there are 20 tasks per hour, since we had 10 students and they were all sending 2 documents in this hour. So which means that 10 times 2, there are 20 tasks in an hour, and obviously in an hour we have 3600 seconds. So if you do the multiplication, you will see that this is actually a time a task waits in the queue. So how are we going to solve or implement this problem? First of all, we need to have a queue of print tasks. As I mentioned in this illustration, this is a queue data structure, so we need to first generate it. And then, since it's a kind of a simulation, we need to keep track of actually seconds. And this is the minimum, actually, the time unit we can play with, the seconds, and the property of the printers in terms of time, let's say some pages per minute, but we can easily convert it to a second. So during this simulation, we will always be doing the operations for each second. And that's why we have a kind of a loop here. For each second, we will be performing the operations underneath. What are they? The first one is when you have a new task in your, let's say, queue, what you do, you simply add it to the queue. And the thing is that you need to have let's say, a property of current seconds. What is that? Let's say you have a print task of P and its time step. You need to have such a property. and this will be, let's say, equal to 23. This will be actually the second you are sending this document to the printer. And then if the printer is not busy, obviously, if there are no items in the queue, then it will be directly printed. But if there are some items in the queue, then the oldest one in the queue will be actually removed and it will be assigned to the printer. But if the queue is empty, then you don't need to do these operations. You can simply transfer it directly to the printer. But if there are some items in your queue, then you should always remove the oldest item from the queue. So this time you need to do another time operation. We know that for our case, you need to actually subtract this time. It was, let's say, 23, and if you are right now at second 43, then you should subtract, and this will be the waiting time for that printer task, for that document. So this is the waiting time of that specific task, and you should compute this one and store it in some kind of a list data structure, so that later you're gonna take the average and tell the average waiting time in the simulation. So after you do all these operations, print all the files, then you can determine actually the waiting times, and you can also determine the printing time with the help of the property of the printer. If it's, let's say, printing 2 pages per minute, and if you have, let's say, 4 pages in your document, and as I said, if the printer has a property of 2 pages per minute, then how many seconds we are going to spend for the printing operation? So 2 pages are processed in a minute, then that means 4 pages will be processed in 120 seconds. Then that will be our printing time. This is printing time, and this was waiting time. And obviously, as you see, we calculate the printing time with the help of the property of the printer, the page per minute number value. But we simply calculate the waiting time with the help of the stamp, the time stamp actually we had taken earlier. Any questions, guys, up to now? Since it will get complicated, make sure that you are with me, you understand what is going on in this simulation.
Teacher, can I ask something?
Sure, go
on. For this situation, first, when we add the item into the queue, we first get the timestamp, and when it left the queue, we get another timestamp and take the waiting time from there, right?
Yep, that's
Okay.
right. This is what you described is here, actually. This is what we do. This is the initial timestamp, and 43 is the current seconds. Yes, this is not timestamp, but this is the current seconds of the, let's say, operation. So we do a simulation. This is the current second, so it's already there. So we simply do the subtraction from this value with the subtract timestamp from the current second. Any other questions, guys? Okay. We are continuing. So now, this time, the printer will be doing 1 second of printing, and we will be actually removing this 1 second from the time required for that specific task. Since we said that we are running kind of a loop for every second, so if 1 second passes, then if you remember in the previous slide, I said that we need to have 120 seconds for the printing operation. But after 1 second has passed, we should say that we have just 119 seconds remaining for the specific printing operation. Then at some point, if the task is completed, and then that means actually the time required is equal to 0. And this time we can easily say that the printer has completed the given task and it's not busy. And I can simply send another task to the printer and start printing another item in our queue data structure. So we repeat these operations until all the documents are printed in the queue. And what we do later, we simply compute the average waiting time and try to give you some, let's say, comments whether the selected printer is a good one or we should find a better printer. Any questions, guys, about the simulations? Now I will show you the example on Python here. This is our printer. Let me make it larger. So obviously we are using the queue data structure. We have a random class. We need to generate a number of actually pages with the help of this random function. And this is we have 2 classes. The first one is about the printer, and the second one is about the task. And lastly, we have a specific definition for the simulation, somehow similar to the previous hot potato simulation. And then we generate some tasks, and here we run the simulation. I will first show you the simulation and then go into details. So as you see, this time we are running the simulation for this amount of seconds, which is equal to an hour. And what about this 2? It should be the pages per minute. So if you use a very low quality printer, a very slow one, an old one, as you see, we have run this simulation for 10 times. And in all of these, the average waiting time is too much. As you see in one of them, each student actually waits an average of 1,000 seconds. And the thing is that in this given hour, it couldn't complete all the tasks. There are, as you see, many tasks remaining. So it's better we increase the quality of this printer. Let's make it 10 pages per minute this time and run the same simulation. So right now, we don't have any tasks remaining, and average waiting times are usually not bad, around 10 seconds, 40 seconds. But if you have some money, maybe you may increase to 20 papers per page, so that we will have usually less waiting times. So here we have a maximum value of 10 seconds here, but it's fine, it's acceptable. So maybe 20 pages per minute as the value we are looking for. Now I will go through all these from the presentation. Any questions, guys? So now let's have a look at the details. I said that we need to have 2 classes, one for the printer, one for the tasks. And in the printer class, we need to keep track of the task assigned and also check whether the printer is busy and we need to also check the time remaining for the current task actually, since we need to do some arrangements. And so it's not that complicated. And for the task, this is a simple task, a single task, not an, let's say, a set of or a queue of tasks, but it's representing a single one. And in that, we need to have the property of pages, the number of pages of this task, and we will be using a random number generator. So let's have a look at the first class, the printer class. This is the initialization part. And as you see, in order to create such a printer, you need to define this property, the page per minute. And we name it here as page rate. And this is given as input. And in the initialization, right now we don't have any task. So the current task is a none, an empty one. And right now, the time remaining for the current task is 0, since simply we don't have any task. But in other case, once the printer is actually doing some printing operation, then the time remaining should be obviously higher than 0, and at each simulation second, it should be decreased by 1. And then what type of operations do we have? We have tick operation. This is a very important one. So it's very similar to second. We are keeping track of in this simulation. If the tasks are not empty, if you have tasks, then what we are doing, we are simply decreasing 1 from the time remaining. Since at the beginning of this printing operation, we know that, let's say, there are 4 pages, and the quality of the printer is 2 pages per minute, then that means we need to spend 120 seconds. So the same thing is actually done here. So this will be the time remaining. And if the time remaining is equal to 0, then we will say that the task is completed and we can assign a non-value to the current task. This is actually the statements we should perform in the tick definition. And then we have another definition called busy. It's not that complicated. We simply check whether the current task is equal to none or not. If it's equal to none, then we can say that it is not busy. But if it has a different value here, then that means it's busy and it's printing some documents. And then we have another definition for the starting of the next printing task. And this is named as start next, and the input is the assigned new task. And we will be using another class task. I will describe it in a moment. So you create a new task with the help of this task class. So you're given input and task input to this definition. So what it does is that it simply assigns this new task to the current task. It was initially equal to none, but right now when you call this definition, the current task will be equal to the new task. And then what we do, we simply calculate actually the time required for the printing of this task. And this is done with the help of the property of our printer. The page rate value, this was given as an input while we were creating this printer class. So what we do in the task class, again, we have an initialization expressions. We need to have a time stamp so that we will be computing the waiting time and the printing times. So once you are creating the task, you should give the current time as an input, and that current time will be stored into the timestamp value of this task. And then what we do, we create a document having a random number of pages between 1 and 20. This is done with the help of this statement. So this is done for the initialization. And then we have some get operations. We get the time value with the help of get stamp operation, and we get the number of pages with this get pages operation. And lastly, we have an important operation for this task class. We calculate the waiting time. And you should call it once this task is actually submitted to the printer. So while submitting it, what we do, we simply subtract a timestamp, which was the property of our task, from the current time. So in our examples, it was 43, and if the timestamp is 23, we do subtraction here. Any questions, guys, about the classes we discussed, the printer class and the task class? Okay, let's have a look at the simulation, how we are running the simulation. So we need to have the property of our printer. We will use it while creating our printer object. This is pages per minute. And then we need to have this number of seconds value. This is the value for how many seconds we are going to do the simulation. So let's go into the details. As I mentioned, we are creating this lab printer with the help of printer class. And we need to have a Q data structure for the assigned tasks. And this is print Q value, print Q variable. And then we have an empty list for storing the waiting times. Since this is important, at the end of the simulation, we will take the average of these values and give the user, give some, let's say, values to the user so that they will conclude whether the selected printer is fine or not. And then here are actually simulation is running within this for loop. For each second in our given number of seconds, we do these operations. If you have a new print task, then you assign a task, actually create a task with the current seconds. And this is the task, and then we submit it to the queue. This is the print queue data structure we created at the beginning of the operation. And then right now here, we will try to do the printing if the printer is not busy. So we check first whether the printer is busy or not. If it's not busy and if the print queue is not empty, then what we do, we remove an item from the print queue with the help of the queue operation, and then try to calculate the waiting time. Since once you remove it and submit it to the print, then that means it's no longer waiting and it's submitted to the printer. So we try to find the waiting time, calculate it, and then assign it to our waiting times list. So if you look at here, we calculate this waiting time with the help of the wait time operation. Let me show you wait time operation here. We do the subtraction, and this is done here with the help of the current second value. This is the current second in our for loop. We calculate the waiting time, assign it, store it into the waiting times list, and then we send an actually task to the printer. As you see, we start the printing task with the help of this start next operation. This was the start next operation. And then after you assign a task to the printer, what you do for each second, at each second, you need to tick, which means that a second will be actually passed, and you need to update some values with the help of the tick operation here. So we are decreasing, as you see, 1 second from the time remaining, since this time remaining has already been calculated with the help of the start next operation. So we simply here subtract 1 second from the time remaining, and we do these operations until we are done with that task operation, printing task. So this is done with the help of ticking here. And after your simulation is completed for the given number of seconds, we calculate the average waiting time and comment it. And also, we also write the remaining task. So this is how we print the result of the simulation to the screen. Any questions, guys? This is how we do the simulation. No questions? Okay, then that means you're all fine. So here there are some extra actually operations. We need to have a proper implementation. This is for generating some random tasks. And as you see, it's generating some random numbers. This is a general layout of our implementation. It's shown you the Python implementation. This is a summary of it. We have a queue class. We have import a random operation for generating the number of pages. Then we have already written the printer class, task class. We do the simulation. We have some tasks generated for the simulation, and then we run it. And we run this simulation, as you see, for 10 times. And the simulations will take about an hour. And the quality of your printer is 5, which means that it's printing 5 pages per minute. Or let me show you once more the Python implementation. So I directly imported to the classes available on the slide, so you can easily do that, do the same. The printer class, the old operations we perform, and the main simulation here, we have some if conditions, a for loop for the given number of seconds. We generate tasks, and with the help of these two simple expressions, we run the simulation. Let's do it with a super printer having 200 pages per minute capability. As you see, the waiting time is almost 0, since the number of pages actually students were printing was between 1 to 20. So if the printer has a capability of 200 pages per minute, then in less than a second, they should be able to print their documents. And obviously, we have no task remaining in this simulation.